Hey Skylar,
What?
I want you to turn your potential energy into kinetic energy.
What?
Just drop in. Back on the topic of conservation of energy. This might look like just a little blue spherical object. This has quite a bit of mass. All right, this is a very dense blue ball. I'm going to take this on this string and it becomes a pendulum. It transfers potential energy into kinetic energy, back into potential, back into kinetic, back into potential. The thing is, if there's no outside forces, the total energy of the system can't change. That means if I let it go from right here, I can be perfectly confident that it's not going to come back and hit me, because it can't come back with any higher than this, because this is the total amount of energy that I've put into it. That energy is going to turn into kinetic energy, turn back into potential energy, then back into kinetic. All right, unless it has an outside force applied to it, it's not possible to have it come back with more potential energy than it left with. So let's demonstrate the law of conservation of energy. All right, here we go. As long as I don't move. Energy is conserved. Physics works. Here we go, sitting down.
Got the energy, man. Bloopers.
Conservation of energy selfie video. Stop. All right, get it down here. Next, we have an example of a simple machine, such as the one shown, and the main principle behind this, which is that you can't get out of doing the work. The work on one side has to equal the work on the other, even though you can manipulate the force. All right, welcome to another edition of Backyard Physics. So here, got a 10-year-old that weighs about 70 pounds.
72.
All right, and myself, that weighs a heck of a lot more than that. Yeah, about 190, so an awful lot more. So how is it that he's able to hold me up on this, don't do that, on this plank? All right, now here is a little clue to how that can work. I'm going to go ahead and try to balance myself on this, and then we're going to use this 10-year-old to lift me up. And hold on, let me get balanced. All right, lift. So and like in this picture here, a small force was exerted over a large distance that moved a large force a relatively short distance. This is called leverage. It's an example of conservation of energy and machines. Is holding me up, but I weigh almost 3 times him, a little less than that. Actually, about a little more than twice his weight is what I am. No, go back to the other. So, how was he able to do that? Now, let's look at the trade-off, because this is conservation of energy. The force of my weight is what he has to lift, but he's able to do that with a smaller force, but he has to do the same amount of work as if he were to lift me this high, because my potential energy is raised to this point. So I have a certain amount of potential energy. That takes a force and a distance. That takes work. He had to do work to get me there, but let's look at this trade-off. Look at the distance that I move compared to the distance that he is moving, and you'll see the trade-off here, how this is able to happen. Go. He is moving a much bigger distance to get me up here. All right, this would not work if this was set up in the middle. It only works when you increase the lever arm. That gives you the mechanical advantage. Oh, you want to try it? You're not going to be able to do it. All right, try. There's simply not a big enough lever for him to get the distance to decrease the force. You can also think about this in terms of torque. We just have not talked about that in class yet. He needs more torque. He needs a longer lever arm. This next bit demonstrates that if I move this boulder to the top of this 2-meter high ledge, doesn't matter how it got there, it will have acquired 200 joules of potential energy, regardless of how it got to that point. The boy's now going to try to pick up this log. We want to take this log and we want to move it up here. I want to raise its potential energy so it's at this point. So one way to do that is what I did. Just pick the log up and put it right here. All right? But I don't think this boy can do that. Hold the log. All right? That's probably not going to happen. Here is a way that the boy can get the log up there. Here we see the trade-off once again, as you can use a large force, the weight of that block of ice, over a short distance of 1 meter, or a small force over the larger distance of the 5-meter long ramp. In both cases, the same amount of work is accomplished.
Inclined plane.
It is an inclined plane. The force is a lot less, but he's having to move at a much greater distance. Either way, the log's going to have the same amount of potential energy at this point. Whether I lift it up and put it here, or whether the boy rolls it along the inclined plane. All right, at this point, thank you. The log has the same amount of potential energy as if I just lifted it to this point. If it falls on your toe from here, it doesn't matter whether I lifted it here or whether he rolled it up the ramp. What the ramp does is it increases the distance, decreases the force, but you can't get out of doing the work. Oh, can Skylar loosen the lug nut? All right, Skylar, try to loosen that lug nut. Now, one thing you can do to automatically help yourself is push at the end of the ratchet. So the ratchet has as long a lever arm as possible, but it is still not moving. All right, here is something we can try. All right, the boy is applying all the force he can muster to pull with. So what we're going to do is apply that force over a longer distance using this breaker bar. So now that force is going to be applied with a longer lever arm over a longer distance. And the lug nut is loosened. All right, a way we could have made that even easier. Let's say it still wouldn't come off and it was still stubborn. We can extend that lever arm even more. What this is doing is extending the lever arm, increasing the torque. It is also multiplying the force at the expense of distance, because if you look at the distance that he is moving compared to the distance that the lug nut moves, the lug nut's moving a smaller distance, but he's getting more force with the expense of distance. So you can think of this in terms of conservation of energy, you can think of this in terms of torque, but what's going on is it's a simple machine. We have increased the lever arm. All right, now to go back on with it, I have this device called a torque wrench, and they usually have long lever arms and they're calibrated so you can tell when you put the proper amount of torque on something. So I can tighten this lug nut, and this will actually click when I've hit a certain amount of torque. And I know it's at the amount of torque that I want, which is about 100 foot-pounds. A study of this image will show how a pulley is also a simple machine. It is a lever. Of energy, I've put together this pulley system. And as you can see, it's got 4 pulleys. Every time the rope goes around the pulley, it decreases the force needed to lift the load by 2. All right? So I can take this, I can sit on it, and the tension in the string is only going to be about 1/8 of what I actually weigh, because down by 2, down by 2, down by 2, down by 2. So it's going down by 2 4 times. 2 times 4 is 8. The part that I had to worry about the most on this was the attachment to the ceiling. The ropes are only supporting 1/8 of my weight. There's actually not a whole lot of tension in the rope. I can use one hand and I can lift myself up pretty easily. I can hold myself. I could even have an 8-year-old. Every time the rope goes around the pulley, it cuts the force needed to lift the object in half. Here it's going around the pulley twice and then coming back around to connect to the pulley. That's a total drop in force of 5, which is a mechanical advantage of 5. A 10-year-old hold me. See that? Can you pull down and pull me up with one hand? And I can pull myself up using this pulley system. And again, have a 10-year-old hold me here. I want to show them with one hand how you can hold me. Okay. All right, now, there is a trade-off as with any machine. And I want to demonstrate that. All right, so what we're going to do is we're going to put the buoy all the way on the ground. So bring it all the way to the ground, and we're going to lift you 1 meter, and we're going to show everybody the trade-off. So get down on there. There's a meter stick in the background. That's not how you sit on it. There's the meter stick behind him. And what I'm going to do is lift him so he is about at the top of that meter stick. All right, he's about at the top of that meter stick. Can you hold this and hold the rope? So he is up 1 meter, and I had to go through all this string. That's about 1 meter, 2 meter, 3, 4, 5, 6, 7. He got raised about 1 meter up. I had to pull 8 meters worth of string. All right, so that's a mechanical advantage of 8. It makes it 8 times easier, but the trade-off is the force is 8 times less, the distance is 8 times greater. And that is conservation of energy. All right, you can't get out of doing the work, but what we can do is do the work with less force, but you have to go a greater distance. Look how all this rope is going to get used up to lower him to the floor. I'm at the end of my rope, and he's on the floor. Conservation of energy.